displacement r at the point of interference would be given by r equals y1 plus y2. When both sources have the same amplitude, then y1 and y2 would be equal to y. When y1 is due the crest or trough, and y2 is also due a crest or trough, the resultant would be the maximum. And when y1 is due to a crest and y2 is due to a trough, or vice versa, the displacement would be minimum.
Experiment. We have earlier discussed the phenomenon of interference of waves. Therefore, it is natural to expect that light also exhibits the phenomenon of interference. But interference of light is not so evident as the interference of sound waves. This is due to the very small wavelength of light waves as compared to the wavelength of sound waves. In 1801, Thomas Young demonstrated successfully the interference of light by performing a double-slit experiment. Young allowed sunlight to pass through a hole and then at some distance through two pinholes, S1 and S2. When light was received on a screen, an uneven distribution of light intensity was observed on the screen. A number of alternate dark and bright spots were seen on the screen. The phenomenon of interference can be
The phenomenon of Newton's rings, named after Isaac Newton, is an interference pattern caused by the reflection of light between two surfaces, a spherical surface and an adjacent flat surface. When a parallel beam of monochromatic light is incident normally on a combination of a planar convex lens and a glass plate, a part of each incident ray is reflected from the lower surface of the lens, and a part, after refraction through the air film between the lens and the plate, is reflected back from the plane surface. These two reflected rays are coherent, hence they will interfere and produce a system of alternate dark and
Diffraction. Sound is propagated in the form of waves. Sound produced in an adjoining room reaches us after bending round the edges of the walls. Similarly, waves on the surface of water also bend round the edges of an obstacle and spread into the region behind it. This bending of waves around the edges of an obstacle is called diffraction. Diffraction is a characteristic property of waves. The waves are diffracted only when the size of the obstacle is comparable to the wavelength of the wave.
See the diffraction pattern for the slit separation that I have over here. Now, the wavelength of the light is that of the helium neon laser, 6328 angstroms. So I gave you the separation between the slit and the screen, which is 200 centimeters. So now you should be able to calculate the slit width from the diffraction pattern. Now, to help you do this calculation, we have on the screen we have markers, and the separation between these markers is 5 centimeters. So they have 5 centimeter markers on the screen. So now you have all the tools to calculate the slit width as I adjust the slit separation. So let me start with very narrow slit where the central lobe is, I can make it almost 5 centimeters or so, and you can see the other lobes, the weaker one. And maybe if we can overexpose a little bit, we can see that indeed there are there's lots of lobes. But if we expose for all of them, then the central one is going to get way overexposed. So in general, we'll be looking just at a few of them. All right, so now let's go back to where we were before, and then we'll start again at a slit width.
Diffraction grating. An arrangement consisting of a large number of equidistant parallel narrow slits of equal width separated by equal opaque portions is known as a diffraction grating. The plane transmission grating is a plain sheet of transparent material on which opaque rulings are made with a fine diamond pointer. The modern commercial form of grating contains about 6,000 lines per centimeter. The rulings act as obstacles having a definite width B, and transparent space between the rulings act as a slit of width A. The combined width of a ruling and a slit is called as grating element.
Polarized wave. The plane determined by the E vector and the direction of propagation of the wave is called the plane of polarization of the wave. If E field remains in a fixed direction, then the wave is said to be linearly polarized or plane polarized. The electromagnetic waves used for radio and TV transmission are plane polarized. The light from sources like the sun or an incandescent light bulb do not show single plane polarization. Let us represent light using the E vector and its propagation as shown. The light from these sources is composed of many directions of the E vector distributed randomly around the direction of propagation of light. This light is transverse but unpolarized. An unpolarized light can be converted into a plane polarized light using Polaroids. A Polaroid consists of a long chain of molecules aligned in a particular direction. The components of the electric vector of the incident light, which are in the direction of the aligned molecules, get absorbed. The direction perpendicular to the direction of aligned molecules is known as the pass axis. That means the pass axis of a Polaroid is the polarizing direction. If an unpolarized light wave is incident on a Polaroid, the Polaroid sheet transmits only that light which has its electric field vector vibrating parallel to pass axis and absorbs the light with E vector vibrating at right angles to pass axis.